Sets of numbers. Now, as we start today, please note this is a very foundational lesson. We're going to talk about a few basic things, but they are pretty important because as we start talking about math and get more detailed with stuff, you are going to be kind of expected to understand subtle differences. So just please keep that in mind. So we start with everything. Oops, there we go. So we start with everything just by understanding that we're really just talking about groups, how we group certain things. Like if I talk about all of the balls on a billiards table, there are 15 balls on a billiards table. 1 through 8 are all solid in color. Technically, the 8 balls is its own little thing. 9 and through 15 are stripes. Okay, fine. What we can do is we can create what are referred to as sets of numbers. Each of the individual ones are each individual number within is called an element. And what we're just trying to do is just trying to note that, okay, based on that, I can group things in specific ways. All balls that are solid, all balls that are striped. Maybe the 8 ball is its own little thing. Kind of depends on that. So when we talk about just grouping things, this is what we're referring to. Sets of numbers are groups, and each little piece inside of each group is what we refer to as an element. Now, just so you know, just because something falls into one set of one set of numbers, for example, which we'll talk about in a minute, doesn't mean you can't fall into many other groups. For example, I could just say, let's just talk about students at King High School. Students at Martin Luther King High School would be one overall group. That's a good solid set of, one big set, I suppose. But if you want to, you can further classify it and get more and more finite and more specific when you talk about sets. Those are called subsets. So like, for example, we could have a big group of set of students at Martin Luther King High School. Then you could have students within Mr. Ariano's math class. Then another subset of students in 4th period in Mr. Ariano's math class. And then you can get even for students in 10th grade in Mr. Ariano's 4th period math class. And you just get more and more and more specific. As you get more and more specific, those are called subsets. And in theory, you could also have sets that have nothing within them. Students who Mr. Ariano doesn't enjoy, who are in Mr. Ariano's math class, who are in 10th grade at King High School. I think I missed that up a little bit, but like you could have sets that have nothing in it. Those are called empty sets. So they do exist. For us, what we're going to start doing, what groups of numbers we're going to talk about, what sets of numbers we're going to refer to are just actual numbers. We're going to group numbers. And we want to know how we talk about them specifically because, well, if I'm being honest with you, as much as I understand in the general parlance, you don't go out talking to people about numbers themselves. It does, as a math person, I suppose, get kind of frustrating when you hear people say numbers are integers and whole numbers and natural numbers and like they're all kind of the same stuff. In actuality, they're not. When I look up here at the number line, those aren't all whole numbers. They're not all natural numbers. There are some finite differences to consider when we look at that. Now, before we get on to the number line, let's just start off with one very basic concept. Until like December, let's just say everything is real. We're just talking about real numbers, numbers that actually exist that we can talk about. Okay, no problem. Every number is a real number. We've kind of heard that. Cool. So how do we break down the numbers, like on the number line? How do we do that? And what are they called? So, number line gone. Let's first talk about just those numbers that were on the number line, the actual numbers that you visually see when you're up there. Because those are the first 3 sets of numbers that we need to think about, because if we can get to those ones, then we kind of make everything else a lot easier. So, the first thing we talk about, as far as I'm concerned, are just the numbers we learn right off the bat. When you're a young kid, you just start at 1, you go to 2, you go to 3, you go to 4. These are the most basic numbers that you think about. They're all positive. You don't even think about negative numbers when you're really growing up. So it kind of makes sense that the numbers that are positive, that we visually see on the number line, those are what we call natural numbers. Natural numbers are the kindergarten numbers, the ones you learn naturally. You just start at 1, you keep going. So 1 is a natural number. 10 is a natural number. 100 is a natural number. If I visually see it actually up there on the number line, I see numbers up there. Those are natural numbers. Okay, cool. That's probably that is the most finite subset, the most specific subset of numbers that we have. Natural numbers. The ones you learn in kindergarten. 1, 2, 3, 4, and so on. So that's the smallest subset. We expand it ever so much with the next set of numbers. Those are called whole numbers. That's when you include the whole. 0. Whole numbers. I know, I'm lame. Here, let me move up here. I'm probably going to get in the way. So, so you notice that what I did was, how about it? There we go. I went 0. I started at 1, and then I just kind of moved a little bit further along the number line to add 0 now to the natural numbers. When I add 0 to the natural numbers, now we're talking about all of those numbers that I now see are what we refer to as whole numbers. So whole numbers are all of the natural numbers plus the whole, plus 0. 1 is a natural number. 1 is a whole number too. So those positive numbers, the numbers in blue that I visually see over there, those are actually, they are the most specific subset of numbers. They're going to be included in all of these for the most part. So those natural numbers are also whole numbers. 0 is a whole number. It's not natural. You know, my family didn't start me at 0. I know there are some people who might have. We didn't. So now we're at whole numbers. All right, and if we finish off the number line, again, we're talking about just the numbers I visually see down there. So we knew the positive numbers were natural. You add the whole to get whole numbers. When I add all of the negatives that I visually see on the number line, those are now called integers. Everything I visually see actually down there is what is referred to as an integer. So 1, again, being the most specific set, 1's natural, 1's whole, 1's an integer. 10, natural, whole, integer. 0, not natural, because you don't start by learning that. 0 is a whole number, and it is also an integer. All the negative numbers, those are integers, but that's it. They're not natural, they're not whole. At one point in time, they weren't even thought to be a thing. We know they are, obviously, now. So those are referred to, so everything we see out there is an integer. So the 3 most specific sets of numbers that we typically think of, that we use in general everyday life, I've actually taken a survey before where it says, enter your zip code as an integer. Like, well, you could say a whole number. You could say a natural number, but no one says that. So they just say as an integer value, which just means basically something you would see on a number line visually. So those are the 3 we talked about. Natural, whole, integers. When you get from there, like that's the big one we want to get to. After we move away from that, now we got to get a little more specific. So obviously we know on our number line right here, we are very aware that there are numbers in between what I visually see. There's decimals, you know. There are 3.5, 7.8, 3.298. What are those called? Because they're not natural, whole, or integers. Those are only numbers that are, I guess, in essence, 0.0. What about anything like that's a decimal? Well, those are either going to be rational numbers or irrational numbers. Rational numbers are, for lack of a better term, any number that can be represented as a fraction. Which means, yes, all of our whole numbers are integers. All of those are also rational numbers as well. We are increasing. Those are finite, more specific subsets. We're increasing the set. Rational numbers, if we're being 100% specific, and by the way, please don't say fraction to your accelerated math 3 teacher or your calculus teacher. They'll smack you maybe. I hope not, but you know. It technically it's a ratio of 2 integers. Integer divided by an integer ratio. If we're talking to normal everyday people that don't really care about math, you just say a fraction, and that's what a rational number is. You could also say a rational number is a decimal that either ends or it repeats at some point in time. Those are other ways to know that it's rational. Irrational, that's everything else. In short, a rational number is something that is a decimal that goes on forever and never repeats. So like pi is the irrational number that the vast majority of people know. E, that's an irrational number. Almost all of the radicals are irrational because they're decimals, go on forever, never repeat, stuff like that. So that's where we kind of now start to diverge. So rational numbers include all of the naturals, wholes, integers, because all of those can be represented as a fraction. They're all over 1. Irrational numbers, not so much. So they're kind of like their own little thing over there. And then, of course, like I said, once you get to that, now everything is real. So when we break it down, before we do that, This is how the symbols for them, by the way. So real numbers are the double strike R, natural numbers are the double strike N, whole numbers are the double strike W. Don't ask me why integers are Z and rationals are Q. I believe, if I'm not mistaken, integers are P, all double struck. Double struck? Yeah, we'll go with double struck, yeah. Okay, so don't ask me about that, whatever. So when I get a visual of everything, this is how we break down all of our numbers. The smallest, most precise set of numbers are natural. You add the whole numbers. You add the negatives on the number line, integers. And then you start getting to decimals. Included in all of those are the rational numbers, fractions. Ratio of two integers. And then irrational numbers, kind of an old thing, but they all fall under the body of real numbers. So, yes, I'm going to expect that you are able to tell me what type of numbers any number of thing is. Bad choice of words, I suppose. If I told you like 4, what is it? It's everything. Oh, sorry, it's not irrational. It's natural, whole, and integer, and rational, and real. -4. Not +4. Once you get -4, now it's not natural or whole. Integer, rational, real. Those are things we need to be able to discern. So we're going to try that. Here I've got several numbers for you. What I'd like you to do is, in a second, you're going to pause the video. You're going to order those from least to greatest, and then tell me what all of them are. What sets of numbers do they fall into? So pause the video, and then when you're ready, restart. Let's see where we're at. We're back. All right, so in order, looks like I only have one negative, so -11.5. I'm converting all of them to decimals, and I'm ordering them all down there. Okay, cool. But what I want to do now is I want to take all of those numbers and see where they all fit in this nice little table down here. I want to classify them into all of their subsets of real numbers. All right, so again, they're all real until December. They're all real. So I know that 2.3 pi, root 5, -11/2, all that. They're all real. But I want to see what else they are. So, okay, let's just start going. 2.3 repeating. It's real. It's a decimal, so it's not going to be a natural whole or integer. So really now the question is it rational or irrational? And this is where we want to know it's a decimal that repeats. The bar tells me it repeats, so it's rational. Cool. Pi, we already know it's real. Everything's real, but it's an irrational number. Again, that's something that goes on forever. It doesn't repeat. Pretty standard. Root 5, same deal. Square root of 5 is like 2.2. I don't know. I'm approximating. It's real because they're all real, but it goes on forever. It never repeats. Most radicals are irrational. Yeah. -11/2. Okay, now we're finally in something that can be represented as a fraction. So obviously it's real. Obviously it's rational. But again, none of these are like visual things on the number line. So I'm not going to, they're decimals. 0.5, that's -0.5, right? So that's all we're going to do. No integer, no whole, no natural. And the last one's actually kind of interesting. I get a few issues with this. Obviously it's real. Everything's real. Until December, everything's real. But there are a lot of people who want to consider that down there irrational because it's got 4 decimal points. No, it's a bit. But, it stops. Granted, it stops after the 2, but it stops. 0.7652 stops. If it stops, it's rational. Remember, irrational goes on forever, never repeats. So that's a rational number. And yes, by the way, I'd like to point out I didn't give you any integers, whole numbers, or natural numbers here. Why? Because they don't all have to be. As a matter of fact, very seldom are they going to be. You're only talking about those numbers you find on the number line. It doesn't happen all the time. Those numbers are not as precise. So just because they're there doesn't mean you have to check some boxes. Be alert. Try it again. Put those in order and then classify them. Pause. Done pausing. Here's the order after I change them all to decimals. Let's go through. Everything's real. Duh. Hey, number 2. That's on my number line. So aside from being real and rational, clearly, let's divide by 1. It's an integer. It's negative. It's on my number line. But that's all as far as it goes because it's not 0. It's not the whole. Nor is it natural. Negatives. Yeah, whatever. We already did pi, if I'm not mistaken. That's real and irrational. Negative 0.321. We're not going to be taken in this time. We know that aside from being real, obviously. It's rational because it does end. 3 decimals doesn't mean much to me. It ends. Hooray. 3 halves, that's going to be, that's a fraction. 3 divided by 2. Ratio of 2 integers. Real, duh, and rational. And then, let's see, negative root 3. Negative root 3 is, well, remember those radicals, with few exceptions, unless they're perfect squares, they're irrational. So that's real and irrational. Easy peasy. But now how do we list all of these things? Because that's the last part we got to do now. So that's where we start talking about notations. So notations are just how we list our sets of numbers. For lack of a better term, sometimes it's how you list answers a lot of times. And we're going to go talk about 3 of them specifically. The first one is the easiest one. It's called roster notation, right? A roster notation is just like what it sounds like. It's a roster. It's a list. Think of my class roster, the roster on a team, just a list of names, right? Well, roster notation, all it does is it says, take those braces, these things, and just list everything in between the braces. So those are all the billiard balls. I just listed them. How many billiard balls are there? 1 through 15. List them all in braces. That's more like parentheses. I don't know how to do braces with my hands. It's weird. I don't know what I'm doing. Hey, braces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Boom, done. So that's roster notation. It's really very simple, but it's kind of limited, to be honest with you. Because, I mean, if you think about it, especially when we talk about numbers, a lot of times you can have literally an infinite amount of solutions if we're talking about like an inequality, for example. That's not really conducive to, hey, let me list every single number that exists in that roster notation. I ain't got time for that. I mean, there are ways to kind of work around it. You can work with both finite and infinite sets. If they're finite, that's when you'd want to actually, like they end and they were kind of short. That's when you'd actually use roster notation probably. You can use infinite sets if you use these ellipses here. List all the natural numbers. No, I'm not going to do that. But 1, 2, 3, 4, okay, ... You can do that. But it's limiting. Just going to be honest with you. Roster notation is probably the least used of all of them. You can use a finite set. You can use an infinite set. You can do all of that. It's just, like I said, you're limited. So we don't use roster notation a ton. Only when we know where it starts and ends. That's about it. More often than not, when we have a little funky, like a group of answers, again, like an inequality, like this, like a number line. Okay, let's just say we want to talk about all the numbers in between 3 and 5, not inclusive of 3 and 5, by the way, but all the numbers in between 3 and 5. If we did that, we would write an inequality like so. 3 is less than x is less than 5. But literally, if that was the solution to a question that we were being asked, we can't use roster notation. That doesn't work. I'm not going to list every single possible number in there. I can't do that. So when we have an inequality, we have another way to write an inequality as shorthand. And it's what's referred to as interval notation. So I'm going to take that exact same inequality that I just discussed. 3 is less than x is less than 5. What we do with interval notation is it's just basically saying, write that interval down there, write your inequality. But instead of putting the little less than or equal to signs, the alligator mouse, never mind. Instead of doing that, we will place them in essence, kind of make them look like an ordered pair, like a point, a coordinate on a graph. And we will use the first and last, the upper and lower bounds, I suppose, of the interval, in this case, which is 3 and 5. So I'm going to put 3, 5. But instead of using 3, 5, and then just automatically putting them in parentheses like an ordered pair, we consider whether or not we are inclusive of the 3 or the 5. One or both, actually. So if you are not inclusive, like we are down here, we are not inclusive, we do not include, we're not equal to 3 or 5. We'll do 3 comma 5, but when we're not equal to, we use braces with respect to that specific bound. So in this scenario down here, it's going to look exactly like an ordered pair, exactly like 3 comma 5, because this parenthesis on each side signifies it's not equal to 3 or 5. If I am equal to, if I put an equal sign here, then I would use brackets. Sorry, I'm going to get brackets and braces mixed up for a minute. Then I'm going to use brackets. So if it's equal to, you use brackets. If it's not equal to, you use parentheses. And that's it. It's just a little bit shorter. It's not much worse. It's pretty straightforward, you know. But that's really all it is. That's really it. Nothing too crazy. We would note that at some point in time you have values that go on forever in one direction, like to infinity. If we do use infinity, if that's the case, we actually never know where infinity is. So since you could never be equal to infinity, if it goes on in that direction, then you would use parentheses in that case. So here's what it's going to look like. And again, you can be equal to in one part, not equal to in another. That's totally fine. That is allowed. So we see here, I'm all of the numbers less than 3. So I'm open dot here, and it goes on forever in the negative direction. So, loud child. Sorry, back. Positive 3 goes on to negative infinity. Well, that means that we are not equal to 3. You can never be equal to negative infinity. So it's going to be like an ordered pair, where the low end is on the left, the high end is on the right, with parentheses inside both of them. Similar thing, all the numbers greater than or equal to negative 2. Negative 2 is the lower end, so that'll be on the left. Infinity is the higher end, so that's on the right. But because we are equal to a value, we use brackets, as opposed to the parentheses, which you're never equal to for infinity. If I have two numbers that are not equal to, it looks just like an ordered pair with a low and high end. And if they are equal to, I use the brackets on both sides. Now again, you can have one or the other. Notice that here. You can have one, you can have both, you can have none. But that's what we're going to do. That's how we use interval notation. It's really very simple. So as an example, hey, 7 is less than x is less than or equal to 12. You could write that. I'm not going to actually pause the video because you're probably doing it in your head. At least you should. It's going to look like an ordered pair. 7 comma 12. But on this side, we have parentheses because it's not equal to. And on the right-hand side, we're going to use the bracket because it is. So really, in interval notation, that's what it looks like. And that's it. Done. Not that hard. What if you have more than one? What if it's in this interval or that interval? What do I do? Well, you do them both. You just write them both. So right here I see -6, -4. Both inclusive, so those be in brackets. And then over there, it's everything greater than 5, not equal to 5. So I'll have 5, infinity, and then, see, parentheses, parentheses. So I'll do both of them. But, and let us be clear, if it's one or the other, and I don't know which one it is, we literally will say interval or this interval. So we literally will just say both with the word or in between because we don't know which one it's in. Now, for anyone who's really very specific, we do have a symbol we use for this. It's if we're doing or, we use a big capital U. That's a kind of a terrible big U, but like, yes, it's called a union. So we do that. If it's one or the other, you could do that instead of using the word or. But frankly, if you just want to use the word or, it's fine with me. Try these. Oh, hold on. A. There we go. Try a couple. Pause the video real quick and answer both A and B, and then come back and see where you're at. Okay, we're back. A goes to negative infinity that way. It includes -1. So negative infinity, comma, -1, parentheses over here, brackets over there because we include that one. Got it? B, x is less than or equal to 2. So negative infinity with parentheses, bracket 2. And then here we have 3 and 11 with parentheses bracket. It's one or the other. We'll say or. So there's 1. Note parentheses for any infinity. It does equal to 2. That works. And then 3, it's not equal to, but 3 comma 11, parentheses with the 3, bracket. Sorry, yes, bracket with 11. And because it could be one or the other, we say or. Yay. Okay, so those two notations are kind of the simple ones. Those are the ones I guess we wouldn't mind because they're fairly straightforward. But in math world, we use interval a decent amount. But if we're going to, let's say we can't do either. Like, what if you wanted to list all of the positive integers that were, I guess I should say, natural, that were all multiples of 2? If you want to do that, you can't do an interval. I guess you could write a roster, but that might take forever. What if you want to be like really specific? That's where set notation comes in, or set builder notation. Let's say, and we're going back to our billiard ball example, we wanted to include all of the numbers that are billiard balls but the stripes. So 9 to 15. 9, 10, 11, 12, 13, 14, 15. How do we do that? So in essence, we just want the numbers 9, 10, 11, 12, 13, 14, 15. We can't use the interval notation because the interval is not continuous. I guess we could list them all like we did down there. But what else could we do? So here's what set builder does. It actually it just emphasizes the variable, and it allows you to be more descriptive. So here's what happens. Inside of braces, you first tell me the variable you're going to use. And you just kind of use the inequality that you would use for interval notation. The only thing with that is that after you do that, you can just and tell me some other information. And here's where all those symbols for specific numbers work out. So here's how this reads. This is the set of all numbers. We're in set builder notation. All numbers are x, such that, that's this line, it means such that. How that line got to mean such that, I don't know. Not quite the promotion. I want all the values that are greater than 8 and less than or equal to 15, which is 9 through 15, if we're talking billiard balls. But, wait a minute. There's a bunch of other numbers, decimals, in between there. How do I further classify? Well, here's where you now can get even more finite, even more specific. That's where set builder comes into play. Oh yeah, all the numbers bigger than 8 and less than 15. Oh, and x. All of those values of x are elements of, that's what this epsilon means. It means they're elements of natural numbers. So all of x values are natural. So I just want the natural numbers. So that's what this is. I just want in essence, it's saying I want the natural numbers in between 8 and less than or equal to 15. That's all you're doing. That's it. Now, this can get a little tricky. There are times you might need to put equations over here because maybe your pattern of numbers isn't just continuous. Maybe you need to, like I said, multiples of 2. Maybe you have to do set an equation of 2n times something. 3n times something if they're multiples of 3. You can get really specific with this. And just so you know, not every notation works every single time. If I want all real numbers but 1, so, set builder notation, you'd like that. They're values of x, but x isn't 1. But you can't write a roster. That's a lot of numbers. We wouldn't do that. And you could write interval. It's in one side or the other. Not equal to 1. Goes to infinity. Negative infinity one direction. Positive in the other. This might be a time I'd want to use set builder notation. Positive odd numbers. I could list with an ellipses. There's no interval because we're only talking about natural numbers. And over here I can be like, okay, every value of x. But x follows a specific equation. 2x minus 1. That's all your odd numbers. But 2x minus 1, that is not discrete. That is continuous. So you'd have to specify, oh, we're only talking about the natural numbers. Yeah. And then numbers within 3 units of 2. So -1 on that way, 5 on that way. I mean, I wouldn't write a roster because there's a lot of decimals. Interval works, and set builder works because I can just use the same inequality that we would use for interval notation. So that's pretty much it. So this is kind of what we're going to do. We're going to practice a little few. So, hey, pause the video when you get a chance and rewrite all of these specifically as they are denoted. See if you can try a few of these. And when you get back, let's discuss. So, pause. Okay, you're back. Okay, I've got a set builder notation in words. Values of x such that x is greater than -5.5 and x are only integers. Okay? Integers greater than 5.5. -4, -3, -2. All of those. Let's see. Positive multiples of 10 in roster notation. Oh, I got to list all of them? Well, if it goes on forever, that's infinite. So 10, 20, 30, 40, 50, ... right? And then I got a set builder notation. This one's simple because it's just an inequality from a number line. So I'll do brace x such that, and it looks like these are x values less than -2. So that x is, less than or equal to with a dot. Okay. X is less than or equal to -2. I guess you could say negative infinity is less than, x is less than or equal to -2, but that's kind of, that doesn't seem right. Yeah, I mean, that's just more work. Shorter work, less work, less work. Yes. Work smarter. Try again. Set all these up. Pause the video. Let me know what you think. All right, let's see. I'm going to write these in words. 2, 4, 6, 8. I'm done. We appreciate. I'm sorry, I'm a dad. Multiples of 2 that are greater than 1 and less than 9. I can do that. What did I write? Even numbers between 1 and 9. Okay, that works too. Cool. Ooh, okay. In roster notation, values of x such that 2 is less than x is less than 8, and x are only natural numbers. X are elements of natural numbers. Greater than 2, less than 8. In roster notation, cool. 3, 4, 5, 6, 7. And yes, by the way, the order in a roster doesn't really matter. You're listing them. Order is irrelevant, but let's be honest. We want to do it in order. And then, okay, set builder notation. Okay, I've got an interval, so we're equal to 99, and then it goes on forever. So brace x such that x is greater than or equal to 99. I guess we could do 99 is less than or equal to x less than infinity, but again, that's more work. So we'll just, do that. Okay. I think that's it. Nothing else too crazy for you. If you got any questions, you know where to find me. Don't hesitate to ask. And be good, y'all.